All right, just takes practice, so let's look at a few more examples. Let's find the value of this integral. All right, so we noticed that right here to find an antiderivative, u substitution is not going to work for us. So let's do the algebraic thing of rewriting square root of t as t to the 1/2 and then distributing. So 2 square root of t, which is 2t to the 1/2. Because I know I'm integrating, I'm going to go ahead and get a rational exponent there. So that's 1/2. Oh, I don't think I made it better. Minus t to the 1st times t to the 1/2, which is t to the 3/2. Okay, and then dt. Ready for integration, that integrand is. So here we go. Let's see. I'm going to keep the 2, keep the t, bump the 1/2 up, increase it to 3/2, and so multiplying by 2/3 here. Minus, I've got t increased by 1 to 5/2. Dividing by 5/2, but multiplying by 2/5 would be a little bit better. And so I'm going to evaluate all of that from 0 to 2. Okay, again, we're paying attention to where we lose the integral symbol. All right, I'm going to clean it up over here. So this becomes 4/3 t to the 3/2 minus 2/5 t to the 5/2. Evaluated from 0 to 2. So I can already tell, as you might, that not the 0 when we're placed in, but the 2 is going to make this kind of tedious. Okay, I'm ready for the evaluation part of the FTC. So let's plug in 2. So what? 4/3 2 raised to the 3/2 minus 2/5 2 raised to the 5/2. Oof. Minus, oh, and how nice. When I replace 0 in here and 0 in here, that's just going to be 0 minus 0, or just 0. So a little bit tedious with the calculations, just to give you some good news here, that if you get to this point and you make a calculation error and it's a free response question, it's not worth that much. They follow your work. It's all about the skill. All right, so let's see if I can kind of take care of this. I know this is going to be 2 cubed. I can't rewrite 2, so 2 cubed, which is the square root of 8, or 8, and then the square root of 8. Or another way to think about this is really pulling a 2 out and multiplying it by the square root of 2. Okay, so I guess I'll just keep 4/3. 2 cubes 8, square root of 8. I'll clean that up in the next step, which will be 2 square roots of 2. Minus 2/5. If you think about 2 raised to the 5/2 power, 2 to the 5th, that would be, there's at least 4 of them. You could pull out a 4 and have square root of 2 left over, but that'll come out in our work. So 2 to the 5th is 32 square root. So square root of 32. That's kind of tedious with these calculations. So 4/3 times 2 square root of 2 minus 2/5. Okay, and this is 16 times 2, or pull out of 4. So that would be times 4 square root of 2. A little bit of cleanup here. A little more cleanup. This becomes, when you multiply 8/3 square root of 2 minus, this would be 4 times 2 is 8/5 square root of 2. That's great. If you wanted to factor out a square root of 2, you could do that. Okay, I'm fine here, but I think you need to be aware of what else you could do, which is to factor out a square root of 2. So that would be 8/3 minus 8/5. And if I saw this, I'd probably want to get a common denominator. So continuing, that denominator being 15. So that'd be 40/15 minus 24/15. Wow. Square root of 2 times, this would be 16 over 15. You could rewrite it as 16 square roots of 2 over 15. Quite a tedious problem after you found the antiderivative. It wasn't the calculus that made this difficult, it was just the radicals and all our previous algebra work and changing its form. All right, let's look at another problem.
I thought you got that on video. I didn't pop on the way.
Okay, looking at this one right here, we're going to switch gears to some trig integrals. Okay, when I think about this being a derivative, I know it's not one of the 6 trig derivatives that I've come to memorize. So there must be something trigonometric that I can do to this problem to simplify it. Okay, noticing the numerator, 1 minus sine squared. That's equal to cosine squared theta, thanks to the Pythagorean property. And is that convenient for us to change? Sure. Because if you notice now, I can divide and have just cosine of theta. Look down at your paper. Have you lost the integral symbol and the d theta? If so, put it on there. Simplifying the integrand. I identify this now as one of the antiderivatives. So if I brought in a negative and pulled out a negative here, this right here goes back to, oh, I lied. I don't need the negative. So sorry. I'm going backwards. Okay. Cosine is the derivative of sine, so this integrates back to sine. So sine of theta evaluated from 0 to pi over 4. Whew. Okay, so take a look at it. We had to do a substitution in here, which allowed us to simplify. Cosine's antiderivative sine of theta. I did lose the integral symbol, the d theta, and so I have 0 to pi over 4 as my limits here. All right, so calculation part. Sine of pi over 4 minus sine of 0. Easy enough. Square root of 2 over 2 and sine of 0, 0, so we're done. So in this example, it kind of changing gears, as you guys can see in example 6. What I did was I looked in the textbook at page 291, just for your reference, page 291. This is problem number 39. Okay. You're going to encounter some problems where you're not given an integral, but you're going to be given a set of equations, and you're going to be asked to find the area of the region that's bounded by the graphs of these equations. Well, if I'm going to find the area, I'm paying attention to the fact that area is positive. That must mean that this region that I'm interested in is above the x-axis. Okay, so I need to set up an integral so that I can use the FTC. Well, to help me set up the integral, a picture is going to be very helpful. So what you'd want to do on these problems on your assignment is use your graphing calculator or your memory of the functions given if you remember what they look like. Okay, real quickly, I can draw a quick sketch that's going to help me, it's going to assist me in setting up the integral. So 3x squared plus 1 is a parabola that opens up, and its y-intercept is at 0, 1, so this is a basic shape right here. Okay, so that's taken care of. I've graphed that. Now y equals 0 is just the x-axis. So just kind of highlighting the x-axis here. That's taken care of. X equals 0 is the y-axis. All right, so just kind of highlighting that. And then x equals 2 is the vertical line right here. So if you think about all of these equations right here and what region they've created, bounded region, okay, you're looking at this space right here. Okay, so they're asking me to find this area. And they're using the word area because area is always positive, and it appeared that this region is above the x-axis. Okay, it's above the line y equals 0 when you compare these two equations right here. Now using my picture, I can certainly set up the definite integral that represents that region. So my lower limit is x equals 0 and my upper limit is x equals 2. I'm accumulating that space between 0 and 2. And so that's what these were for you to recognize that those are the limits. Okay, and so the integral would become 3x squared plus 1. And don't forget your dx. So for me to find the value of this integral, or the area, because it is going to be positive, okay, the exact way to do it is with the FTC. Remember, it's an irregular shaped region. Prior to today, all we could do is divide this into either rectangles or trapezoids and approximate it, because it's not a known geometric shape. And so, but now with the FTC, we can find the exact value. Okay, it's ready for integration. It goes back to x cubed plus x, evaluated 0 to 2. Okay, setting up the evaluation part with the parentheses, plugging 2 in, 2 cubed plus 2. And you gotta love that 0 everywhere you plug in 0, which every term has an x in it, that whole thing's gonna go to 0. 2 cubed is 8, 8 plus 2 is 10, you're done. Okay, let's take a look at one more of those problems too, and the expectation on us as what we need to do. Okay, so for this last example, example 7, again, the directions for this problem, which again, by the way, this is on page 291. Okay, this is something similar that you're going to be asked to do. This is problem 42. You're given this information only, and the directions are: find the area of the region bounded by the graphs of these equations. So compared to the last problem where you were given some x values, notice that you're not given any x values here. It's the picture that's going to provide those x values for you. So either pick up a calculator and graph this in relationship to the x-axis, or think about your background, because you have enough there to graph this equation. Downward opening parabola. Okay, over here, if I were to find the x-intercepts, I would let y be 0 here. I'd factor out an x, or a negative x, leaving you x and then minus, and then a 3. Check your work. You're factoring by distributing. Do I get back to what I had up here? I did. I do. So either negative x equals 0, which means x equals 0, or from this factor, x equals 3. So those are your x-intercepts, 0 and 3. So 0, 1, 2, 3, and 3. And you know it's a downward opening parabola with 2 x-intercepts, so it must look something like this. Okay, so we're asked to find the area of the region bounded by this quadratic and the equation y equals 0, which is the x-axis. So they didn't have to give us our limits because we naturally created this bounded region here. So let's set up the definite integral that represents that region. So the smallest x value is 0 and the greatest was 3. And we're going to integrate the function negative x squared plus 3x. Don't forget your dx. Look down there now, make sure it's there. Both terms are ready for integration. Reverse power rule. Think of that as an exponent of 1, which you'll increase to 2. So you're going to have 3x squared divided by 2. Remember, long ago we lost the constant of integration. Gotta love 0 when you write it down. That makes it convenient, especially if every term of your antiderivative has a 0 in it. Okay, and I'm going to work down here. Okay, so let's find the y value on the antiderivative at 3 and subtract the y value on the antiderivative at 0, and that change in the y's on the regular graph will give us the value of this integral, which represents that region. Okay, notice it's a little baby parenthesis because I know when I plug in 0 here and here, I'm going to get a 0. So plug in 3. So 3 cubed negative 27 thirds plus 3 squared is 9 times 3 is 27 halves. Okay, quick cleanup. This will go down to negative 9 plus 27 halves. And we're kind of committed to this. We should find a common denominator. So that'd be 2. So this becomes negative 18 over 2. Looks like my answer is 9 halves. So fundamental theorem of calculus, how to find the value of an integral, find an antiderivative, the regular function, and then plug in your 2x values to get 2y's on the regular function and subtract them. The change in the y's on the regular function would be the answer to your integral, which gives you this region right here. So big connection, big theorem, and that's how we're going to use the first part of the fundamental theorem of calculus.